As we can see, we are approximating using rectangles. Usually, generally speaking, we can get better approximations with more rectangles. If you approximate with 6 rectangles instead of 2, you're going to be a better approximation. If you approximate with 60 rectangles as opposed to 6, that's probably even a better approximation. Now, it's not guaranteed you get closer to the result with 60 versus 6, but generally speaking, the more rectangles you have, the better approximation, the better the approximation is going to be. When we add lots of rectangles, we don't want to have to stretch out our area notation. You noticed, I hope, that on the problems we've previously done, adding up a bunch of rectangles can take a lot of room on a page. If I had to add up like 60 rectangles, that would take an extremely long summation. Because of this, we want an easy notation for adding things up. Well, it turns out mathematics has done this for us. Oops. The mathematical notation of adding things up is using a capital sigma of whatever it is that I'm adding up. So I'm adding up a bunch of x's. These subscripts are just telling me that's my first x, that's my second x, that's my third x, that's my fourth x, that's my fifth x. Just like I used subscripts with our rectangles. I said we're talking about rectangle 1's length times rectangle 1's width, plus rectangle 2's length plus rectangle 2's width, or times rectangle 2's width. So L1 times W1, L2 times W2, et cetera, et cetera, et cetera. Those subscripts are just the first, second, third, fourth, fifth of whatever it is we're adding up. The notation then says if I'm adding up a bunch of x's, x1 through x5, I take a summation symbol and I say from I equals 1 to 5. So the lower bound is where we're starting our counting, and our upper bound is where we're ending our counting. And this provides a really nice, compact way of writing out, adding up a bunch of things over and over and over again. This is the summation notation we're going to be utilizing in the next bit. Let's use a summation notation to write an approximation of the f of x equals 3x minus x squared on the closed interval from 0 to 3 using 6 rectangles. We'll go back to the right-hand rule that we did earlier. We want to first do the same process that we did earlier. We know that the width is going to be 0.5, and we've already determined the subintervals earlier, 0 to 0.5, then 0.5 to 1, then 1 to 1.5, then 1.5 to 2, then 2 to 2.5, then 2.5 to 3. We already also determined we're going to add up the areas of 6 rectangles, each one of those areas is going to be a length times a width, or height times a width if you want to denote it by height instead of length. Let's therefore rewrite this, because we're just adding up length times width 6 times. I apologize, I had a typo there. Because we're adding up length times width 6 times, we can use our summation notation. So we take A equals, and the summation notation, there is a summation notation up here somewhere, there it is a capital sigma. We're going to write I equals 1 to 6 because we have 6 rectangles. And we write L sub I for the ith length multiplied times W sub I for the width of rectangle I. Now that's the basic idea. We can take it a step further. Because of what the length and width are in this problem, the W of I can all be replaced with 0.5. So the W of I can just be replaced with 0.5 because the width of every single rectangle is 0.5. Now the height of every single rectangle is determined by plugging in the right-hand value into the right-hand value of the subinterval into my function f of x. This is going to be a little bit strange, but think about the length versus the function value of each subinterval. The length of our first rectangle is going to be what we get when we plug in 0.5 into my function. The length of the second rectangle, or the height of the second rectangle, is going to be what we get when we plug in 1 into the function. That pattern is going to go on forever. It's going to be what we get when we plug in something into our function. Notice that when you plug in a 1, you get a 0.5. When you plug in a 2, you get a 1. When you plug in a 3, you get a 1.5. There's a pattern there. Each time you're plugging in a multiple of 0.5. This is 0.5 times 1. 1 is 0.5 times 2. 1.5 is 0.5 times 3. The fourth length is going to be f when I take 0.5 multiplied times 4. So it should tell me f of 2. If you want to generalize that, you take f of 0.5 multiplied times whatever interval I we're at. So that's how you could rewrite this summation notation in a very compact way. Not every time is the thing inside here going to be a really nice function like 0.5 times I. Sometimes it's a little bit different than that, but the widths are all going to be really nice. So when you have this, the widths will be a nice constant number each time.